Hi, welcome to Math with Townsend. This is a video for calculus students who are looking at the optimization part of the course. In this video, I'll be taking up a problem involving a square-based box. Our goal is going to be maximizing volume, and we're constrained by the cost of the materials required to build the box. So here's the problem we're going to work on. Please pause the video so you can read through it. So we know that to start with, what I see that's important is that we have an open box and our goal is to maximize the volume. There's other information that obviously is important, but I always start by saying, what am I maximizing or minimizing, and what can I write in terms of an equation that I might eventually need? So we have an open box and we are finding the greatest volume. So here's an open box. And open, again, just means that there's no top surface. There's a base and four sides only. And I know that the volume of such a thing is length times width times height. So I have a box. I'm maximizing volume. So it's a square-based box. So because it's square-based, the dimensions on the bottom, length and width, are both going to be the same. And if they're both the same, then I'm going to call that x. So I'm going to call this x, and I'm going to call this x, and that means that I can let the height be y. So of course, in a proper word problem, you would see me define that. Let x be the length and width in meters, and let y be the height in meters. But I don't think you need to see me write that in a video. Okay, so that means that because I've now defined my variables, I can rewrite my volume equation using my selected variables. You're certainly welcome to use length, width, height, whatever letters you want, but I like x and y. So now the volume of my box is length times width times height, which is x times y, which is x squared y. That's what I'm trying to maximize. But it's not a function. Volume is not written as a function of x, so I can't yet actually perform the derivative critical point stuff. Which is why we have constraints in the problem. Because if there's no constraints, obviously the maximum volume would be the size of the known universe with 90-degree angles. So the constraints are that I'm constructing the box and it's costing me money, and I only have $72 total. And the sides of the box are $3 per square meter. The base of the box is $4 per square meter. So I need to work that into my constraint equation. So let's talk about my constraint equation. So I always identify it constraint. So we know that the cost is 72. So, my constraint is cost is 72. So let's build an equation which represents the cost of building this box. So first of all, the base. I know that the base is, $4 per square meter. So the base is x times x. So the area of the base is x squared. And then the cost of that would be $4 for every square meter. The sides, so there are 4 sides total. 1, 2, 3, 4. And they're all going to have the same dimension. They're all going to be x times y. So x times y, that's why I put 4 here. And so each of them is x times y. And the cost of the sides is $3 per square meter. So I'm going to write that as 12xy. So $3, and there's 4 of them. That's the 12. Which means I can now write my constraint equation because the cost is $72, and that's going to be the cost of the base plus the cost of the sides. And now I'm going to rearrange that equation so that I have an explicit equation representing what y equals. So I'm going to subtract 4x squared. And then I'm going to divide by 12x. And so now I have a constraint equation explicitly written for y. And because these are all divisible by 4, I'm going to factor out a 4 and simplify, because why not? You should always simplify your fractions. So that's the actual constraint equation that interests me. And because I have my constraint equation, I can go up and I can replace in my volume equation I can replace the y with that constraint equation. So volume as a function of x, it'll be now, is x squared times y. Oops, sorry, that's just an x. So I'm just substituting in the constraint equation for the y value. And this again gives me now a function. Volume is a function of x. And if I clean this up a little, I've got x squared times 18 over 3x minus x to the 4 over 3x. So I have 6x minus 1/3 x cubed. That is my volume equation. And that's the equation I'll be doing the calculus with. I mean, it's all calculus, but I'll be taking the derivative. But before I do that, I always now like to say, okay, let's talk about restrictions. So restrictions, I'm told that no dimension can be less than 1 meter. So that means if you think about the box, that the x value has to be greater than a meter and the y value has to be greater than a meter. But we want our restrictions to be in terms of x. So let's see how we would do that. I'll just put it here because I'm here. So again, originally, we are told that our dimensions have to be greater than 1. So that's what it looks like. But of course, we want our restrictions to be based on x. So I'm going to now take this constraint equation and replace y. And now I have to solve for x in this inequality. And of course, it is a quadratic inequality. So I'm going to have to remind myself some advanced function stuff. So I'm cross multiplying, and then I'm just going to move everything to one side of the equation. And it looks like a quadratic. It is a quadratic, so I'm writing it as a quadratic. And then the way to solve this, I need to factor it. And then this is a quadratic, positive quadratic. It has roots at -6 and a root at 3. So it roughly looks like this. I don't need to make it look any better than that. And I'm looking for where the function is less than 0. So this is where the function is less than 0. So if I was just answering the restriction problem as if that was a separate problem, I would say between -6 and 3. But of course, we're looking at the restrictions on x. And we know that x already has this fact involved. So I'm just going to use this to say x has to be less than 3. And that gives me then my final restriction statement that x has to be between 1 and 3. So thankfully that wasn't more complicated than a simple quadratic, but hopefully you remember how to do that. Okay, now I am ready to take the derivative of my volume equation and find my critical numbers. So the derivative is 6 minus x squared. Set that equal to 0. Solve for x. So I'm going to take the square root of 6. Now I know that there is also the negative square root, but that is completely inadmissible, so I didn't even write it. I mean, and then I did, so, you know. I don't need to see it if I'm your teacher because you are thinking ahead of the game. So now I'm going to calculate the volume at my endpoints of the testing interval and, of course, at my critical value. And what I'm testing, don't forget, is the volume equation. You know, we're not testing the derivative again, but we're testing in 6x minus 1/3 x cubed. So hang on, let me test those. Okay, so I paused the video because you don't need to watch a video of me calculating things. So I can see that the maximum volume is 9.8 right here. It occurs when x is 2.45. And then I do still need to figure out what the other dimension of the box is. So again, I'm going to use this y equals my constraint equation, 18 minus x squared divided by 3x. And I'm going to calculate that y is 1.6 approximately. I know I'm being inconsistent with my decimals. And therefore I can say, therefore the max volume is 9.8 meters cubed when the dimensions are, so the dimension of the box are length, width, and height. So that is the answer to that problem. I hope this was helpful, and keep doing math.